All right, thanks everybody for being here. Thanks to the organizers for putting together this workshop and also for inviting me to speak. Today I want to talk about a problem that's been bothering me for about 5 years now, maybe a little more. And so I'm going to present it to you by the end of this talk, and I hope that by the end of this workshop somebody has some ideas, because then I'll finally be able to sleep a little better at night. So the setup is we're going to talk about posets associated to graphs, which is some of my favorite things to work with. Associated to any finite graph, we're going to assume simple, no loops, no multiple edges, is a poset called the bond lattice. And this is a subposet of the set of set partitions of the vertex set, such that if you look at each block of any partition, it's going to be a connected, the induced subgraph is connected. So for example, if we've got this path on 3 edges, we look at all of these partitions in the bond lattice here, 1, 2, and 3, 4. If I restrict G to the vertex set 1, 2, that's connected, same with 3, 4. But for example, 1, 3, and 2, 4 is not in this bond lattice because 1, 3 is not an edge, 2, 4 is not an edge. If you're into matroids, this is isomorphic to the lattice of flats of the graphic matroid. It's the intersection lattice of the graphic hyperplane arrangement. It controls the chromatic polynomial. All kinds of fun graph stuff is, in some sense, controlled by this poset. And so it's sort of natural, especially considering the venue, to look at non-crossing, the intersection of this bond lattice with the non-crossing partitions of the vertex set. So notice that this depends pretty strongly on the choice of vertex labels, right? This graph here is not the same graph. The graph I had before is the path 1, 2, 3, 4. This graph is 1, 3, 2, 4. And you'll notice that this is a rather different looking poset. And indeed, I say poset because it need not be a lattice. All kinds of properties can, in general, fail to hold. And so these things, as far as I know, and please correct me if there's better information out there, these were first studied systematically by Farmer, Hallam, and Smith in 2020, and around the same time, I looked at some special cases in my dissertation. So I think it was just kind of in the air at the time, and so maybe it's been around before. And so this is not a lattice. If you know a little bit more about matroid theory, the bond lattice of a graph is geometric, so it has all kinds of nice poset properties. These need not have that. It turns out in the special cases I'm interested in, there are nice properties. And the key tool I'm going to use to attack this is poset topology. I am going to say topology. I'm not actually going to do any topology here. I'm suppressing all mentions of the words homology, cohomology, etc. But basically, the tool we want to use is something called EL shellability. And this is a purely combinatorial gadget. You take the edges of the Hasse diagram of your poset. You label each edge with a natural number. You can weaken this restriction, but naturals are fine for now. And then we say that a chain is increasing if the labels strictly increase, as you read from bottom to top, and it's decreasing if they weakly decrease. And this is a key distinction, strictly versus weakly. And we say that lambda is an EL labeling if every interval has a unique increasing saturated chain or maximal chain. And the word that you get by reading the edges is lex least among all saturated chains. This is what's called an EL labeling. And if P has an EL labeling, we say that it's EL shellable. So you think of a lambda word as just like a tuple in order? Lexicographically. Yeah. So EL is short for edge, lexicographic, I think. And so here's an example of one of these, rather than leave it purely abstract. So here we're looking at everybody's favorite poset, the Boolean lattice on 3 letters. I've got the subsets in black and what I claim is an EL labeling in blue. And you'll note, so this is supposed to be some kind of recursive thing. It's supposed to hold for any interval in the poset. But globally, at least, if we read all the words from bottom to top, we see that there's exactly one strictly increasing chain, which is the one that goes from the empty set to 1 to 1, 2 to 3. And, I've labeled this chain, the edges with 1, then 2, then 3. Any other chain, if you follow along, maximal chain, if you follow along, is going to be lex greater than this one. And there's no strictly increasing. Okay? So all of the topology that I'm sweeping under the rug here, by various results of people like Stanley and Bjorner and Philip Hall, and there's a whole very, very beautiful subject here that I wish I had more time to talk about. I love poset topology. But the upshot of all of this is that if you have an EL labeling, you can compute the Mobius function. And the Mobius function up to a sign, which I'm sure I'm off by 1 because I always am. It's the number of decreasing, so remember, weakly decreasing maximal chains in that interval. So if I want to do this sort of Mobius number count, I just have to count these chains with these labels. And frequently, this turns out to be a lot easier than computing the Mobius numbers for big posets, if you have shellability. Okay, so now I want to move to the Ferrers graphs, which I promised in the title. So a Ferrers graph, there's a bunch of different definitions. I think the easiest one is it's a graph whose, you take a Ferrers diagram of some partition. It's bipartite on the rows and the columns, and there's an edge whenever there's an incidence between a row and a column. So for example, here, if I label the columns 1, 3, and 5, and the rows 2, 4, and 6 in this sort of slightly odd, but it turns out useful way, then that's this graph. And sort of, if you want to think about these more intrinsically, just graph theoretically. You fix a finite set of positive integers with an even minimum and an odd maximum, and then you've got an edge from a smaller odd to a bigger even. And it turns out to be the same thing. And these are exactly, it turns out that these are, this characterization here exactly is the class of Ferrers graphs. I mean, up to, different choices of labels can give the same graph, obviously. So these are nice for various algorithmic and enumerative, yeah. Yes, so it turns out that these are what are known as the homogenized lineal arrangement and its generalizations. I can write down the formula, the definition later. Yeah, so this was where they came from. This is where they came up in my thesis as I was studying these hyperplane arrangements. The way that we actually computed stuff is we showed they were graphic. So I'm kind of working backwards. But these Ferrers graphs were invented by Ehrenborg and Van Willigenburg, and they have all kinds of nice properties about orderings on their edges and computing the chromatic symmetric function, all kinds of very beautiful stuff in their paper. And so with Michelle, with Michelle Wax, my thesis advisor, one of the things that we were able to show while I was working on my thesis is we were able to characterize the ordinary bond lattices of these graphs. So you can kind of think about these posets purely intrinsically as set partitions with some kind of parity condition. So the parity condition is in every block, I want the minimum element to be odd and the maximum element to be even as long as the block is not a singleton. So I'm looking at all set partitions, odd minimum, even maximum. Okay. So here's an example of one such. You'll note, okay, if singleton blocks, it doesn't really count, but in each of these odd, in each of these non-trivial blocks, the minimum is odd and the maximum is even. And if you compare, this is the subgraph 1, 2, 3, 4. If you look at its bond lattice. So theorem of Bjorner is that if you're the bond lattice of a graph, you're EL shellable, and hence this poset is always going to be EL shellable, with respect to some nice kind of natural EL labeling that I'm not going to describe. And so the kind of natural question is then, what about in the non-crossing case? So we've already seen that these, this should say poset. These non-crossing bond posets, first of all, they depend very heavily on the choice of vertex labeling, although I've sort of implicitly fixed one here. And they don't need to be lattices. They can lose all kinds of the nice properties that both non-crossing partitions and bond lattices have. So I'm going to let NC star of V be the set of non-crossing set partitions that also have, on V, that also have this parity condition. So the intersection of this with the non-crossing partitions. So for some technical reasons, via a theorem of Bjorner, the EL labeling that I used with Michelle Wax turns out to restrict in a nice way to this NC star of V. So even though in principle these things don't have to stay nice, in our case it does, which is good. So Farmer, Hallam, and Smith also considered this shellability question. They have a bunch of different sufficient conditions for the non-crossing bonds of a graph to be EL shellable. Ours satisfies some, but not all of them. So in principle, you can recover shellability from their results as well. But the choice of labeling I picked lets us reduce things basically down to purely enumerative combinatorics. We can now forget about poset topology almost completely. So to explain the sort of enumeration question that I'm desperately hoping that somebody in the audience will help me solve, I'm going to fix a little bit more notation. So it would have to be something where the unique decreasing chain stays non-crossing, basically. So if you choose an EL labeling such that the one you get consists only of non-crossing partitions, the unique increasing one. So it's kind of what you would hope would be true. So there's a couple, I believe. Any other questions before we? Oh, okay. I'm not as familiar with it, so. Oh, okay. I'm still not sure. Sorry. Okay, so I'm gonna fix some notation. We're looking just at sets of positive integers now. It is a not terribly difficult observation to make that every integer is either even or odd. Well, maybe it's a little difficult depending on what level you're starting, what level of formalism you're starting at. But so every set of positive integers consists of runs of odd and even integers, right? These runs might be of length 1 or greater. If I've got a set V that's like 1, 3, 5, 6, 8, 10, 11, 13, 14, 16. Got 3 odd, 3 even, 2 odd, 2 even. And I'll let the type of a set just be the vectors whose entries are the lengths of these runs. So in this case, the type of V1 is 3, 3, 2, 2. Yeah, so if you start with an even number or end with an odd, they kind of correspond to isolated vertices in this graph. So I'm going to discount it. You get a bunch of zeros, which will go away in the recurrence that I have. Yeah. So it takes a little bit, but not a huge amount of argument to show that this NC star of B, so these non-crossing set partitions with this parity condition, depends only on this type. So, you know, I can kind of shift everything down to be as, given the lengths of the runs, I can make a sort of minimal one. And they'll all have isomorphic non-crossing bond posets. Okay, so here's a recurrence that has haunted me. It's a little nasty. So I'm gonna I wanna count the decreasing saturated chains globally. So I wanna get the Mobius invariant of this poset. So I'll let NA, so I've got some type fractor A. I'll let NA be the number of decreasing maximal chains. And so if I have A equals A1, B1 through AT, BT, the A's are the odd numbers and the B's are so the A's are the lengths of the odd runs and the B's are the lengths of the even runs. I also need down of A is I decrement just the first entry by 1, and A of down by decrementing just the last entry by 1. So this comes from, oh, sorry. Yeah, so it's a little weird. Yeah, well, no, just one entry. So I'm getting rid of a number. So like, yeah, it comes from looking at the ways. Yeah, exactly. Okay, so what one can show is that if you actually start counting these decreasing saturated chains, N of A is N of down A plus N of A down plus, this ought to look pretty familiar to a lot of us. This is pretty clearly a Catalan type recurrence with some twist. And this twist makes things much nastier. And then the boundary conditions are kind of what you want. N11 is 1. It's 0 if any entry is non-positive. And indeed, if you set all the A's and B's equal to 1, you can see that this is exactly the n minus first Catalan number. And just to allude to something in a second, note that Cn minus 1 is 1 over n, 2n minus 2, choose n minus 1. And in the case where they're all 1, I actually have a nice bijection. So I'm not going to explain the details, but here's one of these chains. You label them with a pair of numbers. This represents arcs in the diagram. You then squish these arcs together to get an actual partial triangulation. And it turns out this works, and it's invertible at every step. This is a real pain in the neck, and there's probably an easier way to do all the technicalities that I haven't. But it turns out to give some nice pictures. And so there's a couple of other special cases to consider. Yeah. Yeah. Yeah, so this is just like all the numbers 1 through 2n for some n. Sorry, one more time. Yeah. No. This is the non-crossing. These are the non-crossing partitions inside the bond lattice of this graph. So these also have this parity condition that the minimum is odd and the maximum is even for every block. So they're kind of a weird bipartite analog of the ordinary non-crossing partitions. In this case, that's just when, this is the n equals 2 case. So for n greater than 2, it stops being true. It's too big of a poset to draw. In this case, yes, everything is non-crossing, but I think that should correspond to like 1. No, n1111. Sorry, that's t equals 1. So there's one, yeah, it should be 1. There should be exactly 1 decreasing saturated chain. This one. Yeah. Yeah. Well, it's C and it's the n minus first Catalan number. Yeah. There's lots of weird scaling and index shifting happening, yes. But thank you for the question. Yeah, this is another thing with this thing. There's a lot of, you scale some stuff and then you shift an index and then you scale other stuff. And it's very hard to keep track of if you don't write it down, which is why the notation gets so unwieldy. So what I did want to say is that actually you can solve some more special cases. So if you let just one of the factors be 1, so 1b, 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 or a1, 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 you get this nice kind of deformation of these Catalan numbers. And the proof is only by generating functions in Lagrange inversion. I don't have a bijective proof yet. And correspondingly, I don't have a good characterization of the chains we're counting ought to correspond to some kind of decorated triangulation. But unclear how to do it yet. And the natural last step is, you know, AB, 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 AB. And this recurrence is real bad. You have several coupled functional equations that are nonlinear, but you throw it into Sage and you stare at the numerical evidence and you start throwing diagonals into OEIS, and out pops the following conjecture, which is that the number of these things I want to count is 1 over n times a plus bn minus 2, choose an minus 1. And for a long time, I ended talks like this with, has anybody seen these numbers? But I found them. So this is a special case of some work of Bandrier and Wallner. So this is just the A strictly less than B case, but I bet there's some kind of density argument you can do. We'll let capital AN of K be the number of Dick walks. So that's just using east and north. Starting at the origin under y equals a over bx plus k over b. And we end at bn minus 1, comma an minus 1. And then if I count all of these sets, so some of these walks are counted with multiplicity, I get exactly this binomial business. So my question for the audience, my plea, please, somebody help me find a bijection so that I can stop thinking about these things. Because I can't stop thinking about these things. And that's all I got. I mean, there's plenty of other questions, you know, you can kind of naturally ask, well, maybe if I let these types be arbitrary, then they describe the slopes of some pieces of a curve. You can do other types, you can ask more topological questions, but this is what I really want to know. Thanks, everybody.